January 1977, Berkeley, California. The Lawrence Berkeley Laboratory. Luis Alvarez stood before a geological sample that shouldn't exist. The Nobel Prize winner, awarded in 1968 for his groundbreaking discoveries of elementary particles, had never imagined he would become a detective searching for clues to a 66-million-year-old crime. Beside him stood his son, Walter Alvarez, a Berkeley geology professor who had spent years studying ancient rock formations in Gubbio, Italy. Walter had dedicated his career to understanding a mystery that conventional geology had ignored. Why were dinosaur fossils so abundant on one side of a thin clay layer and completely absent on the other? Now he held the answer. "It's iridium," Walter explained, pointing to the analysis results with quiet intensity. Concentrations unlike anything we've ever measured before. Luis examined the numbers. His eyes, sharp with the precision that had earned him a Nobel Prize, recognized immediately what his son had discovered. The iridium readings were staggering, 30 to 130 times higher than normal concentrations found in Earth's crust. The implication was absurd, impossible. And yet, the data didn't lie. At 76 years old, Luis Alvarez understood that time was running out. He had limited years left to vindicate what his son had found. But he also understood something else. If they were right, this discovery would change how humanity understood extinction itself. Why iridium mattered. The question that consumed Luis and Walter Alvarez in early 1977 was deceptively simple. Where did all this iridium come from? On Earth, iridium is extraordinarily rare. During the formation of our planet 4.6 billion years ago, the heavy elements behaved like stones, sinking in water. Iron, nickel, and iridium, the siderophile elements, migrated downward into Earth's interior, leaving the crust relatively depleted of these metals. The concentration of iridium in the upper layers of Earth's crust is approximately 0.3 parts per billion. Finding it at 30 to 130 parts per billion in a clay layer 66 million years old was like a detective discovering a fingerprint at a crime scene thousands of years after the crime occurred. But fingerprints only matter if you know who left them. Iridium, however, tells a story written in chemistry. In meteorites, the rocky bodies that fall from space, iridium exists in far higher concentrations, approximately 455 parts per billion. In asteroids, comets, and interplanetary dust, iridium is abundant because these extraterrestrial objects formed during the early solar system without experiencing the planetary differentiation that separated Earth's heavy and light elements. Luis Alvarez understood what the iridium layer meant. It was a message from space, a record of material that had arrived from beyond Earth's atmosphere. A messenger carrying information about a moment 66 million years in the past. The question was, when? How much? And what did it have to do with the extinction of 99% of all dinosaurs? The boundary problem. The geological layer they were studying wasn't random. The Gubbio sample came from what geologists called the KT boundary, the boundary between the Cretaceous period, when dinosaurs ruled, and the Tertiary period, when they did not. 66 million years ago, Earth underwent a transformation so complete that it divided Earth's history into epochs. The fossil record told an unmistakable story. The Cretaceous period, lasting 79 million years, ended abruptly. On one side of the boundary layer, the rocks were filled with dinosaur fossils, thousands of species, millions of individual organisms. On the other side, there were none. The boundary was sharp, the division was clean, and nobody knew why. For over a century, paleontologists had argued about what caused this extinction. Volcanic eruptions seemed plausible. They could darken the sky and cool the climate. Mountain-building events could alter ocean chemistry. Maybe diseases swept through dinosaur populations. Maybe evolutionary competition from early mammals, those small furry creatures hiding in the shadows, drove dinosaurs to extinction. Maybe food chains collapsed. Maybe the climate gradually shifted, forcing dinosaurs to migrate to regions where they could not survive. But nobody knew. The boundary layer remained a mystery that conventional geology could not solve. In 1977, as Luis and Walter Alvarez prepared their findings for publication, they proposed something radical. The iridium layer was the signature of an asteroid impact. The hypothesis. Their logic was mathematical and precise. The concentration of iridium in the boundary layer suggested that approximately 10 kilograms of extraterrestrial material had accumulated on every square meter of Earth's surface. If this material represented the dust from a single asteroid impact, working backward from the iridium concentration and the known composition of meteorites and asteroids, they could calculate the size of the impacting object. The asteroid, they calculated, had been approximately 10 kilometers in diameter, large enough to dwarf Mount Everest, massive enough to change the planet itself. The energy released by such an impact would have been inconceivable to human comprehension. A 10-kilometer asteroid striking Earth at approximately 20 kilometers per second would release energy equivalent to 100 trillion tons of TNT, roughly equivalent to 6,000 times the yield of the Tsar Bomba, the largest nuclear weapon ever detonated. Luis Alvarez put it simply. We calculated that the impact would create a fireball that would circle the Earth in 3 days and generate the equivalent of 10 megatons of TNT per square meter of impact area. Such an impact would not merely kill dinosaurs. It would transform the planet itself. It would alter the course of evolution. It would determine which species would inherit Earth and which would vanish forever. The problem nobody wanted to solve. When Luis and Walter Alvarez published their hypothesis in Science magazine in June 1980, the scientific community's response was skeptical, hostile in many cases. Paleontologists, the scientists who had dedicated their lives to studying dinosaurs, were particularly unconvinced. Dr. Dale Russell, one of the most respected paleontologists of the era, publicly stated, "I don't believe the Alvarez hypothesis. The fossil record shows dinosaur populations had been declining for thousands of years before the KT boundary." Geologists who studied volcanism argued that massive volcanic eruptions in the Deccan Traps in present-day India could explain the extinction without needing an asteroid. The eruptions, they noted, were contemporaneous with the KT boundary. Volcanism was a natural mechanism. Asteroids from space were, what? Science fiction? Catastrophism disguised as science? And there was another problem that nobody could answer. Where was the crater? If an asteroid 10 kilometers in diameter had struck Earth 66 million years ago, there should be evidence. A massive impact structure, a scar on the planet's surface, something permanent, something that geologists could see and measure and confirm. But nobody could find one. The debate raged through the 1980s. Hundreds of scientific papers were published, arguing for volcanism, for climate change, for disease, for food chain collapse. The asteroid hypothesis seemed increasingly implausible. Where was the crater? Without the crater, the Alvarez hypothesis was elegant theory without physical evidence. It was a beautiful mathematical solution to a problem that might not require mathematical solutions. Luis Alvarez, now 76 years old in 1977, watched the controversy unfold with the patience of a man who had spent his life solving problems the scientific establishment said were unsolvable. He remained convinced that his interpretation was correct. But he also understood the fundamental principle of science. Extraordinary claims require extraordinary evidence. The iridium layer was extraordinary evidence. But it wasn't enough. The world's scientific community waited for the crater to be found. The unknown signature. What neither Luis Alvarez nor the skeptics knew was that the crater had already been discovered. But it had been hidden in plain sight, camouflaged by geology and time, buried beneath sediment, and ignored in oil company drilling reports. In the Yucatan Peninsula of Mexico, beneath 300 meters of rock and sediment, lay a circular depression in the bedrock approximately 180 kilometers in diameter. It was known to geologists studying the region, documented in oil company surveys, mentioned in academic papers. But nobody had connected it to the extinction of dinosaurs. The crater, eventually named Chicxulub after the nearby village, had been waiting in obscurity for someone to recognize its significance. The scientific evidence existed. The fingerprints were there. The crater was waiting to be recognized. In 1991, more than a decade after Luis Alvarez's hypothesis challenged the world's understanding of extinction, researchers confirmed that the Chicxulub crater had been formed exactly 66 million years ago, at the precise moment of the KT boundary. The asteroid had left its signature everywhere, in the iridium layers scattered across the globe, in the shocked quartz crystals that form only under extreme pressure and heat, in the impact melt rocks buried beneath the Yucatan, in the fossil record showing the sudden collapse of ecosystems, in the geological evidence that had been waiting all along. But it had taken the scientific community 11 years to accept what Luis and Walter Alvarez had discovered with their elegant analysis. 66 million years ago, an asteroid 10 kilometers in diameter had struck the Yucatan Peninsula, and that impact had changed the course of life on Earth forever. The question nobody asked. As Luis Alvarez prepared to see his hypothesis vindicated with the crater confirmation, he understood something that went beyond scientific vindication. The asteroid impact that had killed the dinosaurs had made something else possible. If the asteroid had never struck Earth, dinosaurs would have continued to evolve. They would have diversified further, adapted to new environments, developed new strategies for survival. Mammals would have remained small, nocturnal, insignificant creatures hiding in the shadows of a reptile-dominated world. Primates would never have emerged. Intelligence would never have evolved beyond the level of small, clever mammals. Humans would not exist. The extinction event that had terrified paleontologists as a great catastrophe was, paradoxically, the necessary condition for human existence. The death of dinosaurs was the birth of mammals. The asteroid impact was the cosmic event that made conscious life possible. One question remained unanswered. Could there be another asteroid? Could another impact happen again? The Alvarez hypothesis had revealed an uncomfortable truth. The planet was not as stable as humanity had believed. The Earth was not a static stage for life. It was a dynamic, vulnerable world. Extinction was not something that happened to species through gradual decline or competition. Extinction could happen in an instant. It could arrive from the sky. It could transform everything. And it had happened before. It could happen again. 1978. The Gulf of Mexico, aboard a geophysical survey aircraft. Glenn Penfield was not looking for dinosaurs. He was looking for oil. The geophysicist, working for Petróleos Mexicanos, Pemex, Mexico's state-owned oil company, had been assigned a straightforward task: fly a magnetometer over the coastal waters north of the Yucatan Peninsula and identify geological structures that might contain petroleum reserves. Oil companies understood a fundamental principle of geology. Certain subsurface formations held valuable deposits. Magnetometers, sensitive instruments that detected magnetic anomalies in Earth's crust by measuring variations in the magnetic field, were the tools to find them. Penfield and his colleague Antonio Camargo Zanoguera spent weeks scanning the Gulf of Mexico with their magnetometer, day after day, recording data point after data point. The magnetic readings were supposed to show random variations across the sea floor, a chaotic pattern reflecting the natural geological diversity of Earth's crust. Instead, they revealed something that defied randomness. A vast circular magnetic anomaly emerged from the data. It was approximately 180 kilometers in diameter, so large it would encompass the entire state of Massachusetts. The pattern was unmistakable. The circular symmetry was too perfect to be coincidence. The magnetic intensity was too consistent to be natural variation. It was the signature of an enormous circular structure buried beneath 300 meters of sediment. Penfield recognized immediately what he had found, even though his employer did not. "This is a crater," he told Camargo, studying the magnetic profile. "A massive impact crater. Look at the symmetry. Look at the magnetic intensity gradient. This has to be an impact structure." Camargo nodded, seeing the same pattern emerging from the data. He had studied geology at the University of Mexico and recognized the telltale signature of an impact crater: the circular rim, the magnetic anomaly pattern, the sheer scale of the structure. But neither man understood the broader significance of their discovery. At that moment, in 1978, the Alvarez hypothesis about asteroid impacts and dinosaur extinction was barely being whispered in academic circles. The idea that a cosmic collision 66 million years ago had killed the dinosaurs seemed outlandish to most paleontologists. It flew in the face of conventional geological wisdom. Penfield and Camargo had no way of knowing they were looking at the crater that would revolutionize paleontology and prove that the Alvarez hypothesis was correct. The problem: corporate secrecy versus scientific discovery. When Penfield and Camargo presented their findings to Pemex executives in Mexico City, the response was disappointing. The executives listened politely to the technical presentation. They examined the magnetic data. They understood the implications for geological structure. But they had a singular focus. Pemex had not hired geophysicists to discover historical craters. They had hired them to find oil. The executives made a decision. The circular structure was probably the result of volcanic activity, not an asteroid impact. More importantly, any research about impact craters was irrelevant to petroleum exploration. Research about prehistoric catastrophes would not improve profit margins. The executives classified the geophysical data. The crater remained secret. The discovery was locked away in corporate archives, inaccessible to the scientific community. The magnetic data, the core observations, the implications, all classified as proprietary information belonging to Pemex. For Penfield, the frustration was existential. A geophysicist's career is built on making discoveries that advance human knowledge. Yet here he stood, holding evidence of humanity's greatest catastrophe, silenced by corporate bureaucracy, by economic interests that overrode scientific discovery. He was a man trapped between what he knew and what he was permitted to say. Pemex allowed him and Camargo to present their findings at scientific conferences, they were told, but only with restrictions. They could talk about the crater's general existence. They could describe the magnetic anomaly in broad terms. But they could not reveal the detailed magnetic surveys that proved the crater's existence. They could not share core samples. They could not disclose the specific location with precision. They could acknowledge the crater, but they could not provide the evidence that would allow other scientists to independently verify the discovery. It was a cage built from corporate proprietary protections. The conference that changed nothing. In 1981, at the Society of Exploration Geophysicists Convention in Los Angeles, Penfield and Camargo presented a paper describing their discovery. The presentation included all the data they were permitted to present: the circular magnetic anomaly, the size estimates, the geological interpretation. They titled their presentation, "A Large Impact Crater on the Yucatan Peninsula." The conference room was not packed. The presentation received minimal attention from the assembled geophysicists. There was polite applause, a few questions from the audience, but no sense of urgency. No recognition that they were describing the crater that would vindicate the Alvarez hypothesis. The reason for the limited attention was simple: timing and venue. At that precise moment, across the country in Utah, the Snowbird Impact Conference was convening. The world's leading researchers on impact craters, David Kring, Eugene Shoemaker, Brent Dalrymple, and other titans of impact geology, had assembled to debate whether an asteroid had actually killed the dinosaurs. The debate was intense. The evidence was being scrutinized from every angle. Impact physicists were discussing crater mechanics. Geochemists were presenting isotope analyses. Paleontologists were presenting fossil evidence. The most prominent scientists, the most respected experts, the physicists and geologists who could recognize the significance of the Chicxulub crater, they were all in Utah, not Los Angeles. Penfield and Camargo's presentation, despite its extraordinary content, was overshadowed by conference logistics and academic geography. The most relevant audience for their discovery was not there to hear it. The crater remained unknown to the scientific mainstream. By 1983, Penfield had grown increasingly frustrated. He published a paper in the geological literature describing the magnetic anomaly and proposing it was a large impact crater. The paper generated little response. It sat in academic journals, essentially unnoticed, like a message in a bottle lost at sea. Scientists were searching worldwide for evidence of a crater. The evidence existed, documented, published, waiting to be recognized. But it was invisible because nobody was looking in the right place with the right context. The global search begins. Meanwhile, at universities and research institutions around the world, scientists were engaged in a different kind of search. They were hunting for evidence to support or refute the Alvarez hypothesis. The iridium layer that Luis and Walter Alvarez had discovered was extraordinary evidence, but it needed confirmation. Two major questions haunted the scientific community. First, where was the crater? Second, what other physical evidence could prove that an asteroid had actually struck Earth at the KT boundary? The answer to the second question came from an unexpected source. In the boundary layer at various locations around the globe, Gubbio in Italy, Stevens Klint in Denmark, Caravaca in Spain, and various locations in North America, scientists discovered shocked quartz crystals. These were ordinary quartz grains that had been subjected to pressures so extreme, so violent, that their internal crystal structure had been fractured in a specific pattern. The crystal lattice, normally arranged in regular geometric patterns, was shattered by shock waves traveling through the rock at supersonic speed. Shocked quartz was a signature of violence. It could only form under one set of conditions in Earth's history: the intense heat and pressure of a hypervelocity impact. Volcanic explosions, no matter how powerful, could not create shocked quartz. Meteorite impacts at low speeds could not create shocked quartz. Only the extreme pressures of an asteroid striking Earth at 20 kilometers per second or faster could transform normal quartz into shocked quartz. It was a geological fingerprint of cosmic violence. The discovery of shocked quartz in the boundary layer at multiple locations worldwide was powerful evidence supporting the asteroid impact hypothesis. But it still didn't answer the primary question that haunted geologists and paleontologists. Where was the crater? The scientific community knew an asteroid had struck Earth. They just didn't know where. The crater waits in obscurity. The Chicxulub crater sat beneath the Yucatan Peninsula, waiting. It had been documented in oil company drilling records. It had been noted in geophysical surveys. It had been mentioned, almost casually, in various petroleum exploration reports written by Pemex geologists. But nobody had connected the crater to the extinction of dinosaurs. Nobody had understood its significance beyond its relevance to oil exploration. The crater was like a secret hidden in plain sight. The evidence existed. The geophysical data was recorded. The core samples were preserved. But the scientific community didn't know to look there. They were searching for a crater in the wrong direction, looking in old impact sites, examining ancient geological structures, searching for evidence of large impacts in well-known locations. Glenn Penfield, frustrated and increasingly isolated, held the key to unlocking the mystery. He knew the crater was real. He had seen the magnetic data. He had examined the core samples. But he couldn't share this knowledge with the world because his employer owned the data. The knowledge was imprisoned in him by proprietary restrictions. Time was working against him. The scientific debates were intensifying. The Alvarez hypothesis was gaining acceptance, but slowly, against resistance from paleontologists who insisted dinosaurs had been in decline long before the KT boundary. Penfield knew he possessed information that would settle the debate, but he was powerless to share it. The bridge between theory and evidence. In 1990, a young geologist named Alan Hildebrand was working at the University of Arizona, studying the KT boundary and the evidence for asteroid impact. Hildebrand had been analyzing geochemical data collected from boundary sites worldwide. He was constructing a map of the iridium layer, trying to understand where the highest concentrations appeared. The geographic distribution of iridium might reveal where the asteroid had struck. The iridium concentrations were highest in certain parts of the world, highest in the Americas, particularly in Mexico and the southwestern United States. Hildebrand was searching for an impact crater that was simultaneously very large, 10+ kilometers in diameter, very recent, 66 million years old, and geographically located in this hemisphere where the iridium concentrations peaked. Then, through conversations with colleagues and careful research into published geophysical surveys, Hildebrand encountered the 1981 paper by Penfield and Camargo describing the circular magnetic anomaly in the Yucatan Peninsula. He read it carefully, examining every detail the authors had been permitted to disclose. The location, the size, the age estimates, everything aligned perfectly. The geographic distribution of iridium suggested a crater in the western hemisphere, probably in Mexico. The Chicxulub structure was precisely where theory predicted the crater should be. This had to be it. Hildebrand was certain. He contacted Glenn Penfield directly. Penfield, who had been holding his knowledge in frustrated silence for more than a decade, recognized immediately that Hildebrand understood the significance. He was relieved. Finally, a scientist in the academic community understood what they had found. The door to scientific recognition was opening. Penfield began sharing details about the magnetic anomaly that had been suppressed by Pemex's corporate policies. More importantly, he revealed something that Hildebrand desperately needed: core samples from oil wells that Pemex had drilled through the crater structure during their petroleum exploration operations. These core samples were the key that would unlock the door to understanding the extinction of dinosaurs, the physical evidence of apocalypse. When Hildebrand and his colleagues examined the core samples from the Chicxulub structure, they found exactly what they had predicted based on impact crater theory: shocked minerals, melted rock, and overwhelming evidence of extreme heat and pressure. The cores showed a layer of impact melt rock, stone that had been liquefied by the intense heat of impact, reaching temperatures exceeding 1,500 degrees Celsius, and then solidified again as it cooled. This impact melt rock could only form at the exact location where an asteroid had struck Earth. It was the smoking gun of planetary catastrophe. The cores also revealed tektites, small glassy spherules formed when rock is vaporized by an impact and then condenses in the upper atmosphere. These glass droplets fell to Earth like microscopic raindrops. They had been found in the boundary layer at sites thousands of kilometers away from the crater. Now, studying the core samples from the crater itself, Hildebrand's team found tektites in abundance, evidence showing that material ejected from Chicxulub had been scattered across the entire planet. The scientific chain of evidence was now complete. The iridium layer, discovered by Luis and Walter Alvarez in 1977 to 1980, proved that extraterrestrial material had arrived at the KT boundary and was distributed globally. The shocked quartz, discovered by impact crater researchers in the late 1980s, proved that extreme pressures, consistent with asteroid impact but not with other extinction mechanisms, had occurred at the boundary. The Chicxulub crater, discovered by Glenn Penfield in 1978 but not recognized by science until 1990, proved that an asteroid had actually struck Earth at the precise time of the KT boundary. The core samples, analyzed by Hildebrand's team in 1990-1991, proved that the Chicxulub structure was indeed the impact site. The tektites, found in boundary layers worldwide and in the crater cores, proved that material had been ejected globally and that the impact had been sufficiently violent to spread debris across the entire planet. The case was solved. Dinosaurs had been killed by an asteroid. The evidence was overwhelming and irreversible. Scientific skepticism had been replaced by confirmation. The theory had become fact. The 12-year delay and its consequences. Yet there remained an irony that underscored how close humanity had come to understanding this catastrophe far earlier, and how close it had come to missing it entirely. Glenn Penfield and Antonio Camargo had found the crater in 1978, 2 years before Luis and Walter Alvarez published their hypothesis, 2 years before the world began debating whether an asteroid had caused the extinction of dinosaurs. Imagine the trajectory of science if Pemex had allowed them to share their data publicly. The crater would have been scientifically confirmed years earlier. The Alvarez hypothesis would have been accepted faster and with less controversy. The 12-year period of debate and resistance, the years of publications arguing for volcanism, for climate change, for disease, might have been cut in half. Science would have reached consensus faster. The truth would have been established sooner. Instead, corporate secrecy had delayed the discovery by over a decade. The very technology designed to search for petroleum had accidentally revealed a crater created 66 million years ago by a cosmic collision. But that revelation had been suppressed, waiting in classified oil company files, waiting for a geologist named Alan Hildebrand to make the connection between theory and hidden evidence. The crater had existed all along. It had left its signature in magnetic anomalies and core samples. It had been documented in oil company drilling records and geophysical surveys. It had been waiting beneath 300 meters of ocean sediment and layers of corporate bureaucracy, waiting to be recognized. In 1991, 13 years after Penfield's initial discovery, the scientific community finally accepted that the Chicxulub crater was the source of the extinction event that had ended the age of dinosaurs. The case that Luis Alvarez had opened with his iridium layer discovery was finally closed. The Chicxulub crater was the confirmation that would vindicate 2 decades of debate. The moment of impact reconstructed. To understand what happened 66 million years ago, scientists reconstructed the moment from the physical evidence preserved in the crater structure and the boundary layer. The asteroid was approximately 10 to 12 kilometers in diameter, larger than Mount Everest, more massive than a mountain range, traveling through space at approximately 20 kilometers per second, approximately 45,000 miles per hour. The velocity was incomprehensible, fast enough to cross the continental United States in 160 seconds, fast enough to escape Earth's atmosphere if launched from the surface. It struck the shallow tropical seas of the Yucatan Peninsula in Mexico. The impact energy was incomprehensible to human experience. The energy released exceeded the energy of all nuclear weapons ever detonated, combined, multiplied 1,000 times over. A 10-kilometer asteroid striking Earth at 20 kilometers per second releases energy equivalent to 100 trillion tons of TNT. The explosion created a fireball that expanded outward at supersonic speeds, faster than sound, faster than any aircraft, faster than anything humans could comprehend. In the first seconds after impact, a shock wave traveled outward from the crater at the speed of sound, destroying everything in its path. The blast radius extended hundreds of kilometers. Everything within range was flattened. In the first milliseconds, the impact vaporized the asteroid completely. It vaporized the rock at the impact site. It vaporized ocean water, turning it into superheated steam that expanded explosively outward. The raw crater, the hole left by the impact before the rim collapsed, was approximately 30 kilometers deep and 100 kilometers in diameter. But the shock wave and subsurface collapse expanded that crater to 180 kilometers across. The Chicxulub structure that Penfield would observe in magnetometer data 66 million years later, was the final collapsed form of this catastrophic impact. Shocked quartz, tektites, and impact melt rock were ejected into the upper atmosphere in vast quantities. Some material traveled so high that it achieved near-escape velocity and was scattered across thousands of kilometers. Most of it, however, rained back down over hours and days. The ejecta, the material thrown out by the impact, fell across the entire planet, creating the boundary layer that Luis Alvarez had discovered in Italy and would find replicated at sites worldwide. The darkness that followed, and then came the consequences. Dust and ash from the impact rose into the atmosphere in quantities that obscured the sun. The impact vaporized sulfur-rich rocks in the Yucatan, releasing sulfur dioxide that would combine with water vapor to form sulfuric acid. These acid aerosols, combined with soot and dust particles, began to block sunlight from reaching Earth's surface. Within hours, the sky began to darken. Within days, the sun had become invisible to observers on the surface. Within weeks, Earth had entered a state of near-total darkness, what scientists call an impact winter. Temperatures plummeted as the sun's radiation was blocked by the aerosol layer. Photosynthesis, the process that sustains all plant life and the base of all food chains, became impossible in the perpetual twilight. This was the consequence of the moment preserved in the iridium layer and the shocked quartz crystals. This was the extinction event that paleontologists had struggled to understand for over a century. This was the catastrophe that had ended the age of dinosaurs and determined the future of life on Earth. And the crater had finally provided the answer, waiting in the data that Glenn Penfield had discovered and the evidence that Alan Hildebrand had recognized. The Yucatan Peninsula, 66 million years ago. T-5 seconds. In the upper Cretaceous sky above North America, a 10-kilometer asteroid descended through the atmosphere, traveling at 20 kilometers per second. The space rock had been born in the asteroid belt between Mars and Jupiter, orbiting silently for 4.5 billion years. It had survived the chaos of planetary formation, collisions with other asteroids, and the gravity wells of passing planets. It had journeyed through the cosmic void in complete solitude. And now, on this particular day in geological history, it was about to collide with Earth. The asteroid's surface was scorched black by billions of years of cosmic radiation. Its internal composition was a mixture of rock and metal, rich in iron, nickel, sulfur, and silicon. It was a messenger from the primordial solar system, carrying within it materials older than the mountains of Earth, older than the dinosaurs, older than any creature that had ever walked on land or swam in the oceans. In the final seconds of descent, the asteroid encountered Earth's atmosphere. Friction with the air began to heat the surface. The air temperature around the asteroid reached 10,000 degrees Celsius, hotter than the surface of the sun. But there was no time for gradual heating. The impact was too fast, the kinetic energy too tremendous, the collision too violent for physics to proceed at normal rates. T-0 seconds. Impact. The asteroid struck the shallow tropical seas of the Yucatan Peninsula at 20 kilometers per second. The collision was not a gradual process. There was no slow penetration, no gradual deformation of the crater floor. The impact was instantaneous and catastrophic. At the moment of contact, the asteroid possessed kinetic energy equivalent to 100 trillion tons of TNT. Energy that had been distributed across 4.5 billion years of space travel was released in less than 1 second. The asteroid vaporized instantly. Every atom of the space rock was converted into superheated plasma, a state of matter normally found only in the cores of stars or in nuclear explosions. The rock at the impact site vaporized as well. The ocean water vaporized. Anything within a radius of hundreds of kilometers from the impact point was incinerated. The initial shock wave traveled outward at the speed of sound, a pressure wave so intense that it shattered rock and shredded everything in its path. Everything within 100 kilometers of the impact was destroyed by this initial blast. Forests were flattened as if cut down by an invisible scythe. Creatures were vaporized. The landscape was remade in seconds. The crater that formed was approximately 30 kilometers deep and 100 kilometers in diameter, a hole so vast that it would take the entire island of Manhattan and drop it into an abyss 3 times deeper than the Grand Canyon. But this crater would not remain. The walls of the crater, composed of rock weakened by the shock wave and the intense heat, began to collapse almost immediately. Within minutes, the crater rim had rebounded and expanded. The final crater structure, the Chicxulub crater that geologists would discover 66 million years later, was approximately 180 kilometers in diameter. The seconds after impact, mega tsunami and mega earthquake. But the impact did not destroy only the local area. The energy of the collision was transmitted through the planet itself. The shock wave traveled through the bedrock as if through water. Seismic waves with an estimated magnitude of 10 to 11, far exceeding any earthquake ever measured in human history, radiated outward from the impact site. The magnitude of the energy release was approximately 50,000 times greater than the catastrophic magnitude 9.1 Sumatra earthquake of 2004. The mega-earthquake lasted not for seconds, but for weeks to months, as the planet's crust rocked and trembled from the impact's effects. The shaking was so severe that in the interior of North America, thousands of kilometers from the impact site, the ground liquefied, causing sinkholes to open, landslides to cascade down hillsides, and the landscape to transform visibly. In the shallow seas surrounding the impact site, the ocean water was displaced violently. Mega tsunamis formed, waves of water so enormous they seemed like mountains of liquid moving across the ocean surface. Some tsunami waves reached heights of 2.8 kilometers, nearly 10,000 feet. These waves did not move slowly. They traveled at speeds exceeding 1,000 kilometers per hour, crossing ocean basins in hours rather than days. The mega tsunami generated by the impact traveled outward in all directions. It crossed the Atlantic Ocean and struck the coasts of Europe and Africa. It crossed the Pacific and traveled thousands of kilometers to the Far East. Scientific evidence from 100-plus locations worldwide shows traces of this mega tsunami, sediment layers containing materials from the impact site, mixed with ocean deposits, laid down by waves hundreds of meters tall, traveling at speeds that destroyed everything in their path. On the coasts of North America, facing the Gulf of Mexico, the first tsunami waves arrived within minutes. Waves reached inland for hundreds of kilometers, drowning coastal ecosystems and carrying debris far from the sea. Tsunamis swept away the dinosaurs that inhabited these coastlines. In the interior of North America, the shock waves from the mega-earthquake caused the ground to shake so violently that it turned to liquid, causing surface changes that would persist in the geological record for millions of years. Minutes after impact, the fireball and global wildfires. The impact vaporized not just the asteroid and the rocks at the impact site. It vaporized sulfur-rich compounds in the surrounding rock formations. When rock is vaporized, it doesn't turn into liquid. It turns into gas, a superheated gas that rises into the atmosphere rapidly. This vaporized rock and sulfur rose into the upper atmosphere in a column that reached altitudes of hundreds of kilometers. As it rose, it cooled and condensed. The vaporized material was scattered across the entire planet by upper atmospheric winds in a matter of hours. But before the material could be carried away, it created something even more immediately catastrophic: a fireball. The enormous energy of the impact created a fireball of superheated gas and plasma that radiated outward from the impact site. This fireball did not remain at ground level. It rose into the stratosphere. The thermal radiation from this fireball was so intense that it ignited forests thousands of kilometers away. Across the northern hemisphere, forests caught fire. From Mexico to Canada, From Central America to South America, in Europe and Asia, forests caught fire not gradually through normal combustion, but through thermal radiation directly from the fireball. The fires burned so extensively and so intensely that they created a global pall of soot. Soot particles, microscopic particles of carbon and other organic materials, rose into the upper atmosphere. Hours after impact, darkness falls on Earth. As the fireball cooled and the initial devastation settled, the dust began to rain down. The impact had ejected an enormous quantity of material into the atmosphere. Scientists estimate that 1,500 to 2,600 teragrams, 1.5 to 2.6 billion tons, of soot were lofted into the upper atmosphere by the combination of impact ejecta and wildfire smoke. Combined with this soot was dust, countless microscopic particles of vaporized rock and shocked minerals ejected from the crater. Combined with the soot and dust was sulfur dioxide, which reacted with water vapor in the upper atmosphere to form sulfuric acid aerosols that would persist for weeks. These aerosol particles, combined with soot and dust, began to block sunlight from reaching Earth's surface. These particles rose higher and higher, spreading across the planet through the jet streams. Within hours of the impact, the darkness began. The sun became dimmer. The sky turned orange from the soot particles. Within a day, the sun had become a faint orange disk, visible only as a dim glow through the ash and soot. Within days, the sun had become invisible. Scientists studying this period have concluded that the impact created a darkness so complete that an observer standing in the brightest daylight on the KT boundary morning would have struggled to see their hand in front of their face. The sun did not disappear. It was simply obscured by the veil of soot, dust, and sulfur aerosols that now surrounded the planet. This darkness lasted for days to weeks immediately after the impact. In some regions, the darkness lasted for months. Sediment cores from the boundary layer show evidence of this darkness. Distinct layers of soot, shocked minerals, and other impact debris, followed by evidence of extensive wildfires and ecosystem collapse. Days to weeks after impact, impact winter and ecosystem collapse. With the sun obscured, global temperatures plummeted. The planet began to cool rapidly. Temperatures dropped by an estimated 20 to 30 degrees Celsius in the first weeks after impact. This might not sound catastrophic by itself. Earth has experienced ice ages and climate shifts before. But this was different. This was not a gradual cooling over thousands of years. This was a catastrophic temperature drop in a matter of days. Photosynthesis requires sunlight. As the darkness continued, plants began to suffocate from the absence of light. The oceans, which depended on photosynthetic plankton for oxygen and for the base of the food chain, began to collapse. Marine photosynthesis ceased entirely. As photosynthesis halted globally, oxygen production stopped. Ocean temperatures dropped as the sun's radiation was blocked. Dissolved oxygen levels in the oceans collapsed, creating anoxic, oxygen-free zones where no marine life could survive. On land, the darkness created an apocalyptic environment. Temperatures dropped rapidly. Without photosynthesis, plants died. Herbivores, depending on plants for food, began to starve. Carnivores, depending on herbivores, began to starve in turn. The small mammals, however, possessed an advantage. They could enter a state of torpor, similar to hibernation, and survive extended periods with minimal food consumption. They could slow their metabolic rates and endure the darkness and cold that would kill larger animals. The ecosystem entered what scientists call impact winter. For weeks to months, and in some models for up to 15 years, the Earth remained in a state of perpetual darkness and cold. Temperatures remained below the freezing point of water in most regions. Precipitation patterns were disrupted. Soil moisture decreased by up to 50% in some regions. The forests that had not burned in the initial conflagration began to die from the cold and the darkness. Weeks to months after impact, selective extinction by size. As the darkness and cold persisted, organisms began to die in waves. The extinctions were not instantaneous. They followed a pattern of ecological collapse determined largely by body size. First to suffer were the animals that depended on photosynthesis, the herbivores that ate plants, and the plankton-eating fish and marine animals. As plants died and plankton ceased photosynthesis, these animals starved. The extinction was nearly complete for these groups within days to weeks of the impact. Next to suffer were the carnivores. With their prey populations collapsing, predators found themselves with nothing to eat. Large predators like the famous T-Rex suffered especially. Apex predators require enormous amounts of food, and when prey populations collapse, predators are among the first to starve. Scientists estimate that the largest dinosaurs would have exhausted their energy reserves and starved within weeks of the impact. Dinosaurs, by the time of the KT extinction, were predominantly large animals. The fossil record shows that the vast majority of dinosaur species weighed more than 25 kilograms. Large body size requires more food per day. Large animals starve faster when food is scarce. Small animals, in contrast, can survive longer on less food. They need fewer calories per day. They can enter a torpid state and survive extended periods of deprivation. This size bias in extinction explains an otherwise puzzling pattern in the fossil record. Birds survived the extinction event. Birds are technically considered dinosaurs by modern evolutionary classification. They are descendants of feathered theropod dinosaurs. But birds are typically smaller than non-avian dinosaurs, and birds have the biological ability to enter torpor and survive extended periods of darkness and cold. Small mammals similarly survived because of their reduced caloric needs and their ability to enter hibernation-like states. Within the first few months after the impact, approximately 75% of all species on Earth had gone extinct. The extinction was most severe among large animals, marine reptiles, and organisms dependent on photosynthesis. But it was not absolute. Certain organisms survived: small mammals, some birds, crocodiles, turtles, some lizards, amphibians, and fish in deep ocean refugia. Months to years after impact. The long recovery. The impact winter may have lasted for weeks or months, or in some models up to 15 years. The duration is uncertain. The evidence from the geological record is ambiguous, with different models producing different timelines. What is clear is that photosynthesis failure lasted long enough, months to years, to cause massive ecosystem collapse and the extinction of 3/4 of all species. The oceans began to recover first. As the aerosols settled out of the atmosphere over months and years, sunlight began to return. Photosynthesis gradually resumed. Surviving marine organisms began to reproduce. But on land, the recovery was slower. The forests that covered the Earth in the late Cretaceous would take thousands of years to recover. The large dinosaurs that had dominated terrestrial ecosystems for 165 million years were gone. The ecological vacuum left by their extinction was enormous. Into this vacuum stepped the survivors. Small mammals began to diversify and adapt to the new world without large dinosaurs. Birds, which survived because of their small size and ability to enter torpor, began to evolve new forms and fill new ecological niches. Crocodiles and other semi-aquatic reptiles survived and thrived in the recovering wetlands. This was the beginning of the age of mammals. This was the evolutionary opportunity created by extinction. The very catastrophe that killed the dinosaurs made possible the rise of mammals, and ultimately, the evolution of humans. The irony of survival and human existence. The extinction event that killed 75% of all species on Earth was total and devastating. The planetary climate was transformed in hours. Ecosystems that had existed for millions of years were destroyed. The age of dinosaurs, which had lasted 165 million years, ended in catastrophe. And yet, this catastrophe contained the seed of a new world. The extinction of the large dinosaurs created ecological space for small mammals to diversify and evolve. The extinction of most species allowed the survivors to fill niches and evolve in new directions. 6 million years after the Chicxulub impact, primates, a group of mammals, appeared in the fossil record. 70 million years after the impact, hominins, the ancestors of humans, diverged from their ape-like ancestors. 3 million years ago, the first bipedal human ancestors walked upright on the African savanna. 200,000 years ago, modern humans emerged. 10,000 years ago, humans invented agriculture. 5,000 years ago, humans invented writing. 500 years ago, humans invented the printing press. 100 years ago, humans split the atom. Today, we stand on the edge of space, understanding the very cosmic collision that made our existence possible. None of this would have happened if the asteroid had not struck the Yucatan Peninsula 66 million years ago. The extinction that ended the age of dinosaurs was a catastrophe of unimaginable proportions. But it was also the event that made humanity possible. The death of dinosaurs was the birth of the world that would eventually produce humans, civilization, and consciousness itself. We are the survivors of an apocalypse written 66 million years ago in the rocks and ash of impact winter. December 2024, February 2025, NASA's Planetary Defense Coordination Office, Washington, D.C. In a conference room near the United States Capitol, a group of scientists studied a new discovery with a mixture of fascination and concern. An asteroid designated 2024 YR4 had been identified on December 27, 2024, by the Atlas telescope system in Chile. It was small by cosmic standards, approximately 55 meters in diameter, roughly the size of a 15-story office building. But in February 2025, preliminary calculations suggested a 3% probability that it might strike Earth on December 22, 2032. 3% doesn't sound high, but for an asteroid, it was the highest probability ever recorded for any object tracked by humanity. The asteroid ranked 3 on the Torino scale, the international system used to assess collision hazards. It meant that if 2024 YR4 impacted Earth, the destruction would be real, localized, devastating. But nothing like the Chicxulub impact 66 million years ago. However, the story of 2024 YR4 took an interesting turn. As more observations were conducted in March 2025, NASA scientists used the James Webb Space Telescope to refine the asteroid's trajectory with unprecedented precision. The improved data showed something remarkable. The asteroid would likely miss Earth. On March 8, 2025, the European Space Agency removed Earth collision probability from their models entirely. On April 2, 2025, after 91 days of continuous observation, NASA confirmed that the asteroid would not hit Earth in 2032. But the story did not end there. The refined trajectory showed that 2024 YR4 would pass dangerously close to the Moon, approximately 9,000 kilometers from the lunar surface. By May 2025, calculations showed a 4% probability of lunar impact. While this posed no direct threat to Earth, it highlighted something crucial. Planetary defense is not just about protecting Earth. It is about understanding and managing our entire cosmic neighborhood. The scientists at NASA understood something that most of humanity had forgotten. The Chicxulub impact was not a unique event. It was not a cosmic anomaly that would never repeat. It was the largest impact of its kind, but it was not the only impact. The history of Earth is a history of collision. The statistical reality. Impacts are inevitable. The question that haunted planetary scientists was simple. If an asteroid 10 kilometers in diameter struck Earth 66 million years ago, could it happen again? The answer was undeniably yes. Scientists have calculated the impact frequency for asteroids of various sizes. The data is sobering. An asteroid approximately 1 meter in diameter strikes Earth roughly every year. These small impacts occur constantly, burning up in the atmosphere or striking sparsely populated areas without causing significant casualties. An asteroid approximately 10 meters in diameter strikes Earth approximately once every 500 years. These impacts are more destructive. They would flatten a city or cause regional destruction. The 2013 Chelyabinsk meteor explosion over Siberia, which injured over 1,000 people, was an asteroid approximately 20 meters in diameter. An asteroid approximately 100 meters in diameter strikes Earth approximately once every 11,000 years. An impact of this magnitude would destroy a region the size of a small state or country. It would cause global climate disruption and massive economic damage. An asteroid of this size could trigger crop failures and civilizational stress. An asteroid approximately 1 kilometer in diameter strikes Earth approximately once every 500,000 years. An impact of this magnitude would trigger global climate change, cause crop failures worldwide, and lead to widespread famine and potential civilizational collapse. An asteroid approximately 10 kilometers in diameter, the size of the Chicxulub impactor, strikes Earth approximately once every 100 million years. This is not a coincidence. The Chicxulub impact occurred 66 million years ago. Statistically, another impact of similar magnitude would not be expected for approximately 34 million years on average. Humanity, from this statistical perspective, is currently in a relatively safe window. However, impacts do not follow perfectly random distribution. The mathematics of orbital mechanics is complex, and impacts could theoretically occur at any time, even if unlikely in the short term. But relatively safe is not the same as safe. The 100 million year figure is an average. Small asteroids could impact within decades or centuries. The threat is not hypothetical. It is real and measurable. The debate: Chicxulub versus Deccan traps. For years, scientists debated whether the Chicxulub impact alone had caused the KT extinction or whether multiple factors had contributed to the catastrophe. Some researchers argued that the Deccan traps, massive volcanic eruptions occurring in India at the same time as the Chicxulub impact, had played an equal or greater role in the extinction. The Deccan traps represented one of the largest volcanic eruptions in Earth's history. Over 1.3 million cubic kilometers of lava were erupted. The eruptions would have released enormous quantities of sulfur dioxide and carbon dioxide into the atmosphere. They would have altered climate, acidified oceans, and disrupted ecosystems across the globe. However, modern research has resolved this debate decisively. The evidence shows that the Chicxulub asteroid impact was the primary kill mechanism for the KT extinction. Climate modeling and ecological simulations demonstrate that Deccan volcanism alone would not have caused the dramatic extinction pattern observed. The volcanic eruptions would have created environmental stress, but not the apocalyptic conditions necessary to kill 75% of all species globally. The asteroid impact, however, created exactly the conditions observed: global darkness within days, extreme cold within weeks, photosynthesis failure within months, and ecosystem collapse concentrated in the first weeks to months after impact. Intriguingly, newer research suggests that the Chicxulub impact may have actually triggered the Deccan eruptions. The impact's shock waves, traveling through Earth's crust at the speed of sound, may have triggered the massive magma chambers beneath India to erupt with renewed vigor. In this scenario, the impact and volcanism were not competing kill mechanisms, but rather linked events. The asteroid triggered the very volcanism that reinforced its devastating effects. The asteroid was not the only killer, but it was the primary initiator of the catastrophe. The Cosmic Shooting Gallery. Why Earth Gets Hit. The reason asteroids strike Earth is not mysterious. The solar system is crowded with debris. When the Sun and planets formed 4.6 billion years ago, the process left behind countless smaller bodies, asteroids, comets, and meteoroids, circling the Sun in various orbits. Most of these objects remain in their original orbits, far from Earth. but gravitational interactions occasionally perturb their trajectories. An asteroid in the main belt between Mars and Jupiter might be nudged by the gravity of Jupiter. Over millions of years, the orbit might gradually shift. Eventually, the orbit might intersect with Earth's orbit. When the orbits intersect, collision becomes possible. The probability depends on timing and the precision of the orbital mechanics. Most asteroids miss the planet. But occasionally, the mathematics align and impact occurs. Astronomers have cataloged approximately 25,000 near-Earth asteroids, objects whose orbits bring them relatively close to our planet. Of these, approximately 1,000 are large enough, 100+ meters, to cause regional destruction if they impacted Earth. Scientists continue to discover new near-Earth asteroids at a rate of approximately 100 per month. The challenge is that the solar system contains far more asteroids than humans have cataloged. Current surveys estimate that approximately 90% of the asteroids larger than 1 kilometer have been identified and tracked. But only about 40% of asteroids larger than 100 meters have been cataloged. For smaller asteroids, 10-100 meters, the survey completion is approximately 20-30%. This means that hidden in the cosmic debris surrounding our planet are thousands of undiscovered asteroids, any of which could pose a threat. The story of 2024 YR4 demonstrates this perfectly. It was discovered only weeks before its closest approach to Earth, despite sophisticated global monitoring. The solar system is far larger and more complex than human detection systems can fully encompass. The vulnerability of civilization. Modern human civilization is far more vulnerable to asteroid impacts than the natural world was at the time of the KT extinction. In the Cretaceous, the extinction killed 75% of species, but it did not destroy the planet or render it uninhabitable. Evolution continued. New species emerged. Life adapted and diversified. But human civilization depends on systems that are fragile and interconnected. A regional impact, an asteroid 100+ meters in diameter, striking a city or agricultural region, could kill hundreds of thousands of people. It could destroy critical infrastructure. It could cause global economic disruption through supply chain collapse. A global impact, an asteroid 1+ kilometers in diameter, could trigger crop failures across multiple continents. Agricultural systems dependent on consistent weather patterns would fail. This would lead to widespread famine. It could lead to civilizational collapse and conflict over remaining resources. Billions could die, not from the impact itself, but from starvation and disease in the aftermath. The worst-case scenario, an asteroid 10 kilometers in diameter, another Chicxulub scale impact, would be existential. It would likely trigger human extinction or reduce the global population to a small fraction of current levels. Civilization would collapse completely. The infrastructure of the modern world would be destroyed. Knowledge accumulated over millennia would be lost. The probability of such an event in any given year is extremely low, approximately 1 in 100 million. But over long time frames, the probability accumulates. Over the next 1,000 years, the probability of an extinction-level asteroid impact is approximately 1%. This is not a certainty, but it is meaningful. For comparison, the probability of an airplane crash in any given flight is approximately 1 in 11 million, yet we monitor and regulate aviation extensively. This is not a threat that demands panic. It is not imminent or imminent in any human timescale, but it is real, and it is significant enough that humanity should take it seriously. The planetary defense. Humanity fights back. The recognition of asteroid threat has led to the development of planetary defense, technological and strategic approaches to prevent or mitigate asteroid impacts. The first line of defense is detection. NASA, the European Space Agency, and other organizations operate telescopes specifically designed to search for near-Earth asteroids. The Catalina Sky Survey, the SpaceGuard program, and other initiatives have dramatically improved our knowledge of the asteroids near our planet. The goal is to identify potentially hazardous asteroids decades or centuries in advance, providing time for mitigation. The second line of defense is mitigation. If an asteroid is identified as a collision threat years or decades before impact, humanity has options to deflect it. The NASA DART mission, Double Asteroid Redirection Test, launched in 2022 and successfully impacting the asteroid Dimorphos in September 2022, demonstrated that it is technically feasible to alter an asteroid's trajectory by deliberately crashing a spacecraft into it. The impact changed the asteroid Dimorphos's orbital period by approximately 33 minutes, significantly exceeding the minimum required change of 73 seconds. This proof of concept shows that future asteroid deflection is possible with advance warning. Other proposed mitigation strategies include gravity tractors, positioning a spacecraft near an asteroid to gradually pull it through gravitational attraction. This method is slow but precise, requiring no explosives. Solar sails, using solar radiation pressure to deflect an asteroid gradually. This method works only for small asteroids and requires years of continuous pressure. Ion beams, directing beams of charged particles at an asteroid to gradually change its trajectory. Theoretically feasible, but technologically complex. Explosive deflection, detonating nuclear weapons near, but not directly on, an asteroid to create enough force to deflect it. This is a last resort option because it risks fragmenting the asteroid or creating a worse trajectory. In the case of 2024 YR4 and its potential lunar impact, scientists are exploring whether a deflection mission could be launched to prevent the lunar collision. However, such a mission must be carefully planned. A poorly executed deflection could accidentally nudge the asteroid toward Earth instead. None of these methods would work if an asteroid were discovered only weeks before impact. They require years or decades of advance warning. But with sufficient lead time, humanity likely has the technological capability to prevent an asteroid impact. The paradox: extinction saved us. The final irony of the KT extinction, the asteroid that killed the dinosaurs and created the conditions for human existence, is that it established the very scenario that now threatens humanity. The extinction allowed mammals to diversify and evolve. Humans emerged from this evolutionary opportunity. We became conscious, intelligent, technological beings. And now, the very technology that emerged from our intelligence allows us to detect and potentially defend against asteroids. The organism that the impact allowed to exist may be the only organism capable of preventing future impacts. Dinosaurs could not see the Chicxulub asteroid coming. They could not calculate its trajectory or predict its impact. They could not build spacecraft or deflect asteroids. They were subject to the random violence of the cosmos, with no means to resist. Humans, by contrast, have developed instruments that can see asteroids coming. We have calculated impact probabilities and orbital mechanics. We have created spacecraft and tested deflection technology. We have the means to resist. The universe created the Chicxulub asteroid 66 million years ago, and that asteroid inadvertently created the conditions for human consciousness. Now that consciousness has developed the capacity to protect itself from the very threat that the asteroid represents. This is not destiny. It is not predetermined. But it is the strange and improbable trajectory of a universe where random catastrophes become the seeds of intelligence that can comprehend and defend against future catastrophes. The unfinished story. The extinction 66 million years ago is not a historical curiosity. It is prologue. It is the explanation for why we exist and why we face the challenges we face. It is the answer to the question, why does a cosmic threat matter? Because 66 million years ago, an asteroid struck the Yucatan Peninsula. It killed the dinosaurs. It allowed mammals to diversify. It made possible the evolution of primates, hominins, humans, and civilization. It made possible this moment, sitting in a room at NASA, studying new asteroid discoveries and contemplating whether our civilization can prevent the next Chicxulub. The extinction of dinosaurs was the extinction of one species group and the birth of another. It was an ending and a beginning. It was catastrophe and opportunity. It was the consequence of cosmic violence and the seed of human consciousness. And the story is not finished. The universe continues to orbit. Asteroids continue to move through space. Impact remains inevitable at some time scale. The only question is, will humanity be ready? Will we maintain vigilant detection systems? Will we invest in planetary defense technology? Will we act decisively when a threat is identified? The answer to those questions will determine the next chapter of Earth's history.